Hi, I'm Eric. I'm a PhD candidate in the Department of Materials Science and Engineering at the University of Toronto. I'm sitting in front of the Pickering Nuclear Generating Station, where every day the buildings behind me produce thousands of megawatts of electricity quietly and reliably to serve the people of Toronto and beyond. And yet, the conditions inside of the reactor are harsh, much harsher than the stormiest, windiest days on the Great Lakes. As nuclear engineers, we must ensure the safe and reliable operation of nuclear power plants by understanding the mechanisms by which damage to the materials they are made on occurs. This damage is a picosecond scale and nanoscopic phenomenon known as displacement cascades.
Displacement cascades are initiated by kinetic energy imparted to the atomic structure of a material by incident energetic mass of particles, that is, neutrons or nuclei. These events produce atomic scale damage, typically point defects, whose accumulation and evolution results in engineering scale changes to the material. The rate at which radiation damage is accumulated can be modeled as inversely proportional to a parameter called threshold displacement energy. This parameter can be thought of as the energy required to displace a single atom from its lattice site. The ab initio molecular dynamics simulation at the right illustrates a possible trajectory in which an 800 electron-volt hydrogen nucleus imparts a maximum energy of 50 electron-volts to a tungsten atom near a 100 surface, via a surface-adsorbed oxygen atom. The tungsten atom that receives maximal energy in this sequence is the second atom to collide with the oxygen atom. In this work, we will examine the effect of incident hydrogen ions near the threshold displacement energy on the mechanical properties of tungsten. Threshold displacement energy is expected to vary substantially with crystallographic orientation. In recent work by Bigmastar, a machine learning-informed interatomic potential has been used to simulate TDE scale events in tungsten across a fine sampling of crystallographic orientation space to produce the mapping shown here. The large increase of TDE near the 3-2-1 direction is expected on physical grounds due to geometric considerations of the BCC lattice, and the prediction of TDE in high symmetry directions is consistent with prior studies. The substantial variation in TDE with crystallographic orientation has the engineering implication that we may be able to employ crystallographically textured materials to manage radiation damage. The motivation for the experiments presented here is to use recrystallized polycrystalline material as a platform to attempt to observe the orientation dependence of TDE, by employing characterization methods with intergranular specificity on specimens of material exposed to irradiation conditions near the threshold displacement energy. Amongst the distribution of grain orientations in a polycrystalline material, we may expect to see certain grains more or less affected by radiation damage if the irradiation condition is above or below the TD in the surface normal crystal direction of each grain.
In the Fusion Materials Laboratory at the Institute for Aerospace Studies, we're interested in the materials which would be used to create next-generation nuclear reactors, particularly nuclear fusion reactors. In the experimental reactor ITER, tungsten will be used as a component called the diverter, which will be subjected to hydrogen ion irradiation in various energy regimes, from edge plasmas at energies below the displacement damage threshold, but by hydrogenic charge exchange neutral particles at energies near and exceeding the displacement damage threshold. In this work, I've prepared tungsten specimens, carefully prepared to a mirror finish, and irradiated them at energies at or below where it is expected to see displacement damage. In previous work with this accelerator, a signature of displacement damage has been detected at irradiation by deuterons at 800 electron volts in the form of increased hydrogen absorption at energies associated with displacement damage traps.
The specimen is mounted behind a tungsten mask to create a well-defined area of interest. The specimen is electrically isolated from the mask and a 30-volt bias is applied to suppress secondary electrons so that beam current can be accurately measured as flux. Typical beam flux is 10 to the 18 per meter squared second, and specimens are irradiated to 5 times 10 to the 23 per meter squared fluence. Mechanical and electropolishing produce a smooth surface with grain boundaries visible to optical microscopy. Typical grain size is 100 microns plus or minus 50. The mask size is large enough to target dozens of grains, and the grain size is large enough to target several nanoindentation measurements per grain. Therefore, the material can be characterized before and after irradiation with granular resolution. Since it is expected that 800 electron-volt deuterons will produce displacement damage, a sequence of energies decreasing from there is examined. To test lower kinetic energies, the isotope is changed to protium, and the accelerating voltage is decreased to 500 volts. To contextualize the energy regime, the table below lists the particle momenta for each irradiation condition, and a calculation of the energy transfer due to an ideal head-on collision. Head-on collision energy transfers are calculated for a 2-body case with hydrogen hitting a tungsten, and for a 3-body case with hydrogen hitting an oxygen which then hits a tungsten. Downtown, at the Department of Materials Science and Engineering, characterization techniques are applied to understand the effect of irradiation. Specifically, nanoindentation is a micromechanical test used as a surface-sensitive probe of the near-surface mechanical property evolution, and electron backscatter diffraction is used to measure grain orientations in the recrystallized tungsten.
Nanoindentation applies a fine diamond tip at very small and highly controlled loads to the surface of a specimen. And in the case of radiation damage by hydrogen ions near the threshold displacement energy, it allows us to probe to a depth comparable to what is expected as a result of the irradiation process.
Nanoindentation is performed at 2 loads, 5 mN and 14 mN. The low load produces smaller impressions that can be more densely spaced within a grain. However, in unirradiated material, the low load sometimes results in a purely elastic response and sometimes results in an elastic plastic response. At 14 mN, the nanoindentation impressions are reliably plastic. After irradiation at higher energies, it is typically observed that 5 mN impressions leave an observable plastic impression, and the effect of irradiation energy on incipient plasticity will be further examined in this work. In the example, grain shown here, half of the pre-irradiation 5 mN tests are plastic, while after irradiation, 100% of impressions are plastic. Out of 184 impressions made pre-irradiation, only 33% were plastic, while after irradiation, out of 165 impressions, 99% were plastic. As a side note, the example grain shown was situated near the edge of the mask during irradiation because fine alignment of the specimen in the mount is difficult. The darker region at the bottom is typical of the area directly outside the masked region with a boundary generally defined by the mask but with some preference for grain orientations. This grain also develops blister-like features which are typical and seem to be associated with surface normal orientations near 111, but surface blistering has not been more closely explored in this work. Approximately 3,500 nanoindentation tests were performed and manually classified and quantified by their load displacement response. The parameter which is extracted will be referred to as yield load, and whose measurement is schematically illustrated by the green circles in the diagram. Cases 1 to 4 are typical of unirradiated material or material irradiated by lower energy hydrogen. Cases 5 and 6 are typical of material irradiated at higher energy. To do justice to the large scale of nanoindentation testing performed, the data are presented in a somewhat unusual way. Let's take a moment to explain this plot representing a single specimen before we compare irradiation energies. Each data point marker represents an individual nanoindentation test. The yield load described previously is plotted on the y-axis, and the x-axis represents the sequence in which each test was performed. Larger grains can accommodate more impressions and consequently occupy more room on the horizontal axis. The data are grouped into series by the identification descriptor given to their grain. The purely elastic cases are represented with a break in the y-axis, labeled unyielding. For the example case of 800 electron-volt protium, we can observe our finding that irradiation promotes the onset of plasticity in the stark difference of population size above and below the break in the y-axis. Furthermore, we can see that 24 grains have been tested, that there are an average of 6 or 7 indents per grain, that the average yield load after irradiation is around 2 mn, and that large grains with many indentations exhibit similar variance to small grains. We can see that individual grains are not uniformly susceptible to pop-ins before irradiation. However, we cannot quantify a yield load for the unirradiated material. When we examine the data from the 5 mN testing of each specimen, a clear trend in reduction of yield strength with increasing irradiation energy is apparent. Specimens irradiated by 500 and 600 electron-volt protium do not show an obvious difference in their response to 5 mN loading before and after irradiation. The gross characterization is that there is no observable effect on their yield load and it exceeds 5 mN. At 800 electron volts, protium irradiation induces a yield load reduction to around 2 mN, and deuterium irradiation induces further yield load reduction to around 1 mN. The 600 and 800 EV per H specimens were also tested with 14 mN loading. This ensures that the unirradiated material will usually yield, allowing a better comparison of the effect of irradiation. With the higher load testing, it is seen that the lower energy irradiation has an effect of lowering the yield load by 10 to 20%, whereas the higher energy condition lowers the yield load by 80 or 90%. A single specimen was returned for a second irradiation to take it to effluence 3 times higher. 5 grains were large enough to accommodate a third round of nanoindentation characterization. Hydrogen retention is expected to be saturated at these fluences, so the effect on yield load is thought to be a result of accumulation of radiation damager rather than an effect of hydrogen implantation. It is worth examining the hardness measurements from these indentation tests, because that is a commonly reported parameter from nanoindentation investigations of radiation damage. It is found that there is a small observable effect of radiation-induced hardening in these specimens, but unlike with the yield load measurement, which showed the weakening effect clearly, the hardening effect is smaller than the variance in measurements within a grain. This is rational because the radiation damage layer has a nanoscopic extent, and the yield load measurement is taken from a sampling of the material at a penetration depth of tens of nanometers, whereas the hardness measurement is taken from a penetration depth of hundreds of nanometers. It is therefore suggested that when using nanoindentation, yield load is a more sensitive indicator of radiation damage than hardness.
With these measurements, we believe it is clear to say that nanoindentation is capable of resolving damage to tungsten at energies near the threshold displacement energy. Anecdotally, we have not observed a strong dependence of yield load reduction with crystallographic orientation. We believe that this is explained by the production of damage being mediated by a particle of intermediate energy on the surface, for example, carbon or oxygen, being involved between the collision of the hydrogen and the tungsten. This would randomize the direction that the kinetic energy is imparted, and a strong crystallographic variation in TDE, as has been suggested by others, would not be clearly observed in this type of experiment. We suggest that our results are consistent with a spherically average threshold displacement energy around 40 electron volts. And in summary, the main contribution is that we are able to detect radiation damage at its energetic onset.
The data presented in this video have not explicitly examined the orientations of individual grains. Without getting into details, EBSD has been used to identify grains of similar orientation, and they have been grouped according to predicted TDE for their orientations. The pink crosses indicate the orientations of grains in 2 example irradiation cases, and the blue lines indicate the groupings that have been made. No clear differences in post-irradiation mechanical response have been observed amongst groupings. For more details, please await the forthcoming manuscript, or contact the author directly.